Hi everyone, my name is Yang Yu. Let me introduce my research. My research is fast and efficient AI. I'm a presidential young professor at the National University of Singapore, and I got my PhD from UC Berkeley. In the last few years, we know AI models are becoming more powerful, but they are also more expensive to train, especially computationally expensive. So here is the year. In the last few years, here is the training cost. Even though the single floating point operation per dollar is becoming lower, which means the single floating point operation is becoming cheaper, but the total cost is much higher. We need high-performance computing, HPC techniques to make AI models training, fine-tuning, and inference more efficient, and cheaper and faster. That's my research. So, what's the key problem? We reviewed the product strategy of NVIDIA for the last 5 years. I know NVIDIA has many great strategies and many fancy techniques. But what is the most important product strategy for NVIDIA in the last few years? The key strategy is to put more HBMs in the same physical space. From a 100, H100, H200 to B200. You see, they just put more HBMs. We know HBM is good for large AI models. However, HBM is off-chip. That means we have physical distance. With physical distance, potentially, we have higher latency. That's a very big concern. So, how can we make full use of NVIDIA chip the growing performance? How can we make full use of the GPU servers? We need massive parallelism. The massive parallelism is the only solution we can use to maximize the performance for hundreds or thousands of GPUs. That means NVIDIA needs very high parallelism from the software level to hide the latency. We have better hardware, but we need very high software parallelism, and then we can achieve the best performance. Without parallelism in the software, we cannot maximize the performance of the hardware today. So, my research is to design and implement empirical methods to make AI run faster and more efficient. That's high-performance computing for AI. Specifically, the focus of my research is to extract more parallelism from AI workloads to mask the hardware latency. To extract more parallelism, I designed system-level techniques, algorithm-level techniques, and optimizer-level techniques. Let me use one example to introduce my research. Lars and Lamb. Firstly, let me introduce large batch training. Assuming every iteration you use 2 million tokens to train your model, you need 400 million iterations. How about now? You increase the number of tokens by 10 times per iteration. You also reduce the number of iterations by 10 times. I mean, with a larger batch or more tokens per iteration. Potentially, you can make full use of more GPUs, but you can also reduce the number of iterations. It's a double win, right? It's a win-win solution. However, the concern here is, if you make the batch size very large, often you converge to a bad minima, like a sharp minima with very poor generalization. We want something like a flat minima with better generalization or a stable solution. With a sharp minima, even if you can train faster, the model quality is very bad. We want to avoid sharp minima. Even if we want the model trained faster with large batch training using more GPUs, we cannot accept sharp minima because the model quality is just terrible. To solve this problem, I proposed the Lars and Lamb optimizers. The key idea of Lars and Lamb is the trust ratio. So, for the image or video model, like we use Lars, the trust ratio example is the norm of weights over the norm of gradients for each layer. We compute this dynamically, and then we use this important navigation to help the model to train stably and very efficiently for very large batch sizes. And also, we used a similar idea for Lamb. By doing so, the model can train very fast with a very aggressive learning rate, and all the layers can be very stable. Eventually, we converge to a very good minima. So, here is the key idea of Lars and Lamb. With better navigation, we can train faster, and also we converge to a flat minima. We want to avoid the sharp minima. We train fast, and also we are stable. That's the key idea of Lars and Lamb. Here are some of the applications of Lars from the year 2015 to the year 2020. People reduced the ImageInit training time from 29 hours to 30 seconds. So, since 2017, all of them actually used Lars. Lars was used by Tencent, Sony, Google, Fujitsu, and Google. A few years ago, Google trained for the first time their AI models with 4,000 TPUs. So here is the paper from Google. They also used Lars and Lamb for training their AI models. Snapchat used Lamb to train their video generation model, Snap Video. So here is the paper from Snapchat with Lamb. They can train the model with a large batch, make it more stable and more scalable. Also, the convergence is better. Also, from NVIDIA's public GitHub, we can see Lamb can be 17 times faster than state-of-the-art solutions. So here it's from a media public GitHub. Also, MobileNet v3 is one of the most downloaded AI models. In June of 2025, this model was trained by Lamb. Also, US DOE Oak Ridge National Lab, they used Lamb. They can make the training 60% faster. And Facebook Perception Encoder. All the core trainings are using Lamb. You see, for image pre-training, video fine-tuning, distillation, all of them use LAM. LAM is also implemented in Microsoft DeepSpeed. LAM is Shopify CTO's favorite optimizer. And also Benjamin Mann, who is the co-founder of Anthropic and also the co-first author of GPT-3 when he was at OpenAI. Before he trained GPT-3, he used LAM to scale the transformers to 128 GPUs for the first time. This was very important for the early study. Even for today, you can search on the internet. Google used our LAM to reduce the BERT training time from 3 days to 76 minutes. And after LAM, we also designed and implemented some new optimizers. We won the ACL and 2 AI Distinguished Paper Awards. Even for today, LAM was used by Microsoft DeepSpeed, ByteDance Megascale, 10,000 GPU cluster, and also NVIDIA. We also trained our own model by our own infrastructure software, by our optimizers' training tactics, right? That's OpenSora. Its OpenSora got over 26,000 GitHub stars. And we minimized the training cost. We just used $200,000. Very efficient. And we put everything together, build the Colossal AI software. Colossal AI has ND parallelism, tensor parallelism, large-scale optimizer, and memory management, fast inference. Colossal AI is very good software for training AI models. Colossal AI has got 46,000 GitHub stars, similar to DeepSpeed and NVIDIA Megatron. So here is the AI infrastructure overview. Firstly, we have the hardware and low-level software, cluster management, inference software. So Colossal AI is here, and then AI frameworks, and then the AI models. My research is in this level. We build HPC techniques to make AI models run faster and more efficient. It's high-performance computing for AI. So here are some of my research awards. I was nominated by UC Berkeley for the ACM Dissertation Award. Only 2 students were nominated by Berkeley. And I won the Presidential Young Professor Award at NUS. It's a highly competitive tenure-track position. For early career faculty. And I also won the IEEE CS Early Career Award for HPC. And I won the ACM George Michael HPC Fellowship. This was the only PhD fellowship on the ACM homepage in 2017. And I also got the award for research. When I graduated from UC Berkeley, I also won some paper awards. Firstly, I was the corresponding author. My student is the first author. Treble AI, ACL, ICLR, CVPR. Myself is the first author on ICDM, ICPP, and IPDPS. Thank you.